This conference will now be recorded.
Good morning, all. We will start with a session. Can anyone confirm if I'm audible and is my voice clear?
Yes, ma'am, your voice is clear and audible.
Okay. So today I'm going to give a demo on DFT, which is nothing but design for testability. So before we go into what is DFT, let's first try to understand what is VLSI. So VLSI stands for Very Large Scale Integration. So VLSI stands for Very Large Scale Integration. Large Scale Integration. So it means implementation of million transistors in a small area. So goal of VLSI is nothing but high performance. So ensuring faster processing, and then low power. So optimizing the power usage to extend the battery life. Optimizing the power usage to extend the battery life. Okay. And then low area. So reducing the chip size to achieve compact products. Low area is reducing the chip size. Reducing chip size to achieve compact products. Okay. So this is what. So high performance, ensuring faster processing. Low power, so optimizing the power usage to extend battery life. And low area, reducing chip size to achieve compact products. And this is how our chip will look like after it has been manufactured. And next, let us try to discuss on ASIC flow. So ASIC stands for Application Specific Integrated Circuit. So this is the full form of ASIC. So ASIC stands for Application Specific Integrated Circuit. So which means it is an IC that's custom designed for a particular application. So it is an IC that's custom designed for a particular application. That's custom designed for a particular application. For a particular application. So that is what is ASIC. So the full form of ASIC is Application Specific Integrated Circuit. So it is actually an IC that's custom designed for a particular application. So say for example, a modem chip. It can't be used as a chip which is used for deployment of airbag in automobile. So a modem chip can't be used as a chip. Can't be used as a chip, which is used for deployment of airbag in automobile. Which is used for deployment of airbag in automobile. Deployment of airbag in automobile. So that is what is an example. So ASIC means Application Specific Integrated Circuit. It is an IC that's custom designed for a particular application. So say for example, a modem chip, it can't be used as a chip which is used for deployment of airbag in automobile. And ASIC flow means it basically gives the steps which we need to follow for designing the chip. So that is what is ASIC flow. So ASIC flow means it basically gives us the steps. Okay, Kapil's screen display has some color issue. Like, how about others? Are others also facing the same issue? Like one person has told in the chat box that he's facing some color issues while screen sharing. Does anybody else face the same issue? You can let me know. Is
No,
my
ma'am.
screen
It looks good.
okay? So yeah, I think Kapil, you are facing some issue. Can you like log off and re-log in and see? Okay. So yeah, now let's continue. So ASIC full form is application specific integrated circuit. It is an IC that's custom designed for a particular application. So say for example, a modem chip, it can't be used as a chip which is used for deployment of airbag in automobile. So a modem chip, it can't be used as a chip which is used for deployment of airbag in automobile. So ASIC flow means it basically gives the steps which we need to follow for designing a particular chip. And in the upcoming slides, we will try to see the various steps which is involved in the chip design. Okay. So the first step would be is this design specification stage. So the first step will be the design specification stage. So based on the application for which we are designing the chip. So based on the application for which we are designing the chip. Based on the application for which we are designing the chip. For which we are designing the chip. Okay. So certain specifications like how many memory modules. Okay. So certain specifications like how many memory modules, how many memory modules, and then processors, and then sensors are required, and then what has to be the power, what has to be the power. So all these kind of specifications will be decided. Okay, so in the design specification stage, so based on the application for which we are designing the chip, certain specifications like how many memory modules, processors, sensors are required, what has to be the power. So such kind of specifications will be decided during the design specification stage. Now, after the design specification stage, we have the design code stage. So the design team, they will be writing the design code of the chip. So design team will write the design code of the chip. Will write the design code of the chip. Design code of the chip. Okay, so design team will write the design code of the chip. So they are basically describing the functionality of the chip. They are describing the functionality of the chip. Describing the functionality of the chip. Okay, so design team, they will write in behavioral model and then in data flow level model. So design team will write in behavioral model and in data flow level model. Will be writing in behavioral model and data flow level model. So there will be various styles of modeling in Verilog. So we have the behavioral and data flow level model. So design team, they will be writing the design code in behavioral model and data flow level model. Okay, so design team, they will write the design code of the chip. They are describing the functionality of the chip. So design team will write in behavioral model and data flow level model. And then after the design team, we have the verifications team. Verification, it is actually to validate the functionality of the design to ensure that it meets the required specifications and performs as intended. So verification, it is actually to validate the functionality of the design. So it is used to validate the functionality of the design. Validate the functionality of the design to ensure that it meets the required specifications. To ensure that it meets the required specifications. It meets the required specifications and performs as intended. And performs as intended. Okay, so this is nothing but the verification stage. So it is to validate the functionality of the design to ensure that it meets the required specifications and performs as intended. And after the verification stage, we have the synthesis stage. So in the synthesis stage, what will happen? The behavioral model and data flow level model code. So the behavioral model and then the data flow level model code. Data flow level model code. So earlier we had this one, right? The code was actually written in behavioral model and data flow level model. So the behavioral model and data flow level model code, so that will get converted into structural form. So that will get converted into structural form. Okay. Or we can even call it as the technology node specific gate level netlist. It will get converted into structural form, or we can call it as technology node specific gate level netlist. Okay. So the behavioral model and then the data flow level model code. So that will get converted into structural form, or we can even call it as the technology node specific gate level netlist. So this is what. So first we had the behavioral and data flow level model code, right? So the behavioral model and data flow level model code, it will get converted into structural form, or we can even call it as technology node specific gate level netlist. And after that, we have the design for testability team, so which we will discuss about it in the next slides. We will discuss about design for testability team in the next slides. And after that, we have the physical design team. So physical design team, what do they do is they will be converting this gate level netlist into layout form. So in physical design team, the gate level netlist will be converted into layout form. So the gate level netlist is converted into layout form. Is converted into layout form. So that is what is a physical design team. So the gate level netlist is converted into layout form. Okay. And then next we have the sign off. So in sign off, we have three things. One is STA. So STA stands for static timing analysis. Static timing analysis. So that is what is STA. STA stands for static timing analysis. And then we have PV. So PV stands for physical verification. Physical verification. And then we have LEC. And then we have LEC, which is nothing but logical equivalence check. We have LEC. So the full form of LEC is logical equivalence check. Logical equivalence checks. Okay. So STA stands for static timing analysis. PV stands for physical verification. LEC stands for logical equivalence check. Okay. So first coming to what is STA. So STA full form is static timing analysis. So as its name suggests, it is the method of validating the timing performance of a design by checking all possible paths for timing violation. So it is the method of okay, one second. I'll just complete this slide and then I will take up the questions which is there in the chat box. Yeah, I'll just complete this slide and then I'll just check if I'll just check if there are any questions in the chat box, and then I will address the questions which is there in the chat box also. Yeah. So STA stands for static timing analysis. So as its name suggests, it is a method of validating the timing performance of a design. So it is a method of validating the timing performance of the design. Validating the timing performance of the design. Timing performance of the design. Of a design by checking all possible paths for timing violations. By checking all possible paths for timing violations. Okay. So STA stands for static timing analysis. So it is a method of validating the timing performance of a design by checking all possible paths for timing violations. And PV stands for physical verification. It is actually to verify the layout of the circuits. Okay. So it is actually to verify the layout of the circuits. To verify the layout of the circuits. Okay. And then LEC stands for logical equivalence check. So logical equivalence check. So why it is actually done is, our design, it actually undergoes a lot of changes in each stage, as you have observed in that ASIC flow slide. So our design undergoes a lot of changes in each stage. Our design, it undergoes a lot of changes in each stage. Lot of changes in each stage. Okay. So which means first we had the behavioral and data flow level model code. So first we had the behavioral and data flow level model code. Okay. And then that was got converted into a technology node specific gate level netlist. So that got converted into a technology node specific gate level netlist. Gate level netlist. Okay. And then later like DFT and also if some special cells for low power design, if you're going for low power design, then some special cells for low power design will also be added. So special cells for low power design. Low power design like isolation cell clock gators will be added. Isolation cells clock gators will be added. Okay. And then we will also be DFT team also we will be adding our own test structures. So DFT test structures will also be added. Okay. So DFT test structures are added. DFT test structures are added. Okay. So this is what. So our design, it undergoes a lot of changes in each stage. Like first we had the behavioral and data flow level model code. So that got converted into a technology node specific gate level netlist. And then certain special cells for low power design like isolation cells, clock gators, all those things will be added. And then DFT test structures are added. Okay. So that is why LEC is actually done. So therefore, LEC is done to check whether the final design is logically equivalent to the original design. Okay, so LEC is done. LEC is done to check whether the final design. To check whether the final design, whether the final design is logically equivalent to the original design. Is logically equivalent to the original design. Okay. So actually LEC will be performed after each stage, like after synthesis, after DFT insertion, after PD, like that. So LEC will be performed after each stage. LEC is performed after each stage. After each stage. So like after synthesis and then after DFT insertions, after DFT insertions, after PD, like that. Okay, so that is what is LEC. So LEC full form is logical equivalence check. So our design undergoes a lot of changes in each stage. Like first we had the behavioral and data flow level code, as now we have seen in the ASIC flow slide, right? First we had the behavioral model and data flow level model code. So that got converted into technology node specific gate level netlist. And then certain special cells for low power design like isolation cells, clock gators, all those things will be added. DFT test structures are added. So if you see, LEC is actually done to check whether the final design is logically equivalent to the original design. Okay, our design is undergoing a lot of changes in each stage. So therefore, LEC is done to check whether the final design is logically equivalent to the original design. And LEC will actually be performed after each stage, like after synthesis, after DFT insertions, after PD, like that. Okay. And then we have tape out. So tape out means delivering the database to the manufacturing unit is what is called as tape out. So delivering the database to the manufacturing unit. So that's what is called as tape out. So delivering the database to the manufacturing unit. To the manufacturing unit. So that's what is tape out. Delivering the database to the manufacturing unit. And then we have this packaging and testing. So packaging and testing, it is actually done after manufacturing. Packaging and testing is actually done after manufacturing. Okay, so we have the packaging and testing. So packaging and testing is actually done after manufacturing. Okay, so basically what is this packaging and testing? So packaging means, so this is this like if you see this complete circle is nothing but a wafer and each small portion in it is called as a die. Okay, so covering this die with a protective layer is what is called as packaging. Covering this die with a protective layer is only called as packaging. So packaging means covering the die with a protective layer. So packaging means covering the die with a protective layer. With a protective layer. So that's what is called as packaging. So packaging means covering the die with a protective layer is called as packaging. And testing means it is actually to check if our chip is good or not. So testing means it is actually to check if our chip is good or not. That is to check whether there are any manufacturing defects or not. So testing, it is actually to check if our chip is good or not. Good or not. That is to check whether there are any manufacturing defects or not. That is to check whether there are any manufacturing defects or not. Whether there are any manufacturing defects or not. Okay, so that is what packaging means. Covering the die with a protective layer is called as packaging. And testing is actually to check if our chip is good or not. That is to check whether there are any manufacturing defects or not. Okay. So now let's try to understand in the upcoming slides. We will try to understand more in detail about what is verification, what is design for testability, and what is this testing. So we will try to understand these three things more in detail in the upcoming slides. So what is this verification, what is DFT, and what is this testing? Let's try to understand about it in the upcoming slides. So DFT means It is actually to insert test structures in the design during the pre-silicon stage. So pre-silicon stage means before manufacturing. Pre-silicon stage means before manufacturing. Okay, so DFT is to insert test structures in the design during the pre-silicon stage. So pre-silicon stage means before manufacturing. Okay, to facilitate means to help detection of manufacturing defects in the chip. To help detection of manufacturing defects in the chip. So which means if suppose a particular chip fails after manufacturing. Okay, so if suppose a particular chip fails after manufacturing, DFT engineers will be able to tell what manufacturing defect has caused the chip to fail. So if suppose a particular chip fails after manufacturing, a particular chip fails after manufacturing, DFT engineers will be able to tell. DFT engineers will be able to tell what manufacturing defect has caused the chip to fail. What manufacturing defect has caused the chip to fail. Okay. So DFT is to insert test structures in the design. Like we will be adding our own test structures. Okay, like scan insertions, MBIST insertions, boundary scan insertions. Like that we will be adding our own test structures in the design. So we will be adding our own test structures like scan insertions, MBIST insertions, boundary scan insertions. Like that. DFT is actually to insert test structures in the design. Like we will be adding our own test structures like scan insertion, MBIST insertion, boundary scan insertion in the design during the pre-silicon stage. So pre-silicon stage means it is nothing but before manufacturing. Okay. So to facilitate, that is to help detection of manufacturing defects in a chip. So if suppose a particular chip fails after manufacturing, DFT engineers will be able to tell what manufacturing defect has caused the chip to fail. Okay. So role of DFT engineers. So role of DFT engineers as we discussed in the previous slide. Okay, so before we proceed further, let me just once check the chat box because when I'm presenting, I will not be able to simultaneously see the chat box. So let me once check the chat box. Like do we do synthesis without tickle scripting? Tickle scripting means which one you are asking? We will be making use of the DC specific commands. DC tool synthesis will be performing it using the DC tool. So we will be making use of the design compiler tool, DC tool, the synopsis synthesis tool for performing the synthesis in our DFT labs. So tickle scripting means which one you are asking? Sumansa. In our labs, we will be performing synthesis at one point. So we will be making use of the scripts, which is specific to the design compiler tool, which is nothing but the synopsis tool for performing synthesis. So we will be performing like synthesis at one stage in our DFT labs. So there we will be making use of that DC tool, synopsis DC tool specific synthesis commands. We will be making that script. We will be making use of it in order to perform the synthesis in our labs. Okay. Okay, so now let's go ahead here. So what is the role of DFT engineer as we discussed in the previous slide? So DFT is to insert test structures in the design during the pre-silicon stage to facilitate detection of manufacturing defects in the chip. So that is what we had discussed it in the previous slide. So DFT is to insert test structures in the design during the pre-silicon stage to facilitate detection of manufacturing defects in the chip. Now, DFT engineers do not check the functionality of the chip. We rather check the quality of the chip. So DFT engineers do not check the functionality of the chip. We rather check the quality of the chip. So what does that mean? Let's try to understand here. Okay, what does that mean? Let's try to understand here. Okay, so DFT engineers do not check the functionality of the chip. We rather check the quality of the chip. So what does that mean? Let's try to understand. Consider a half adder design. Okay, consider a half adder design. The equation for half adder will be sum is nothing but A XOR B, carry is nothing but AB. So whether this is correct or not, this is what will be checked by the functional verification team. So they will be checking the functionality. So by mistake, if someone has written sum is equal to A plus B, carry is equal to AB, this will not function like a half adder. So this is what will be checked by the functional verification team. They will be checking the functionality. Okay, so if you consider a half adder design, so for half adder, sum will be A XOR B, carry will be AB. So whether this is included or not. So sum will be equal to A XOR B, carry will be equal to AB, whether this is correct or not. So that is what will be checked by the functional verification team. They will be checking the functionality. So by mistake, if someone has written sum is equal to A plus B, carry is equal to AB, this will not function like a half adder. So this is what will be checked by the functional verification team. They will be checking the functionality. Now DFT team, we do not check the functionality. DFT team, we do not check the functionality. We check whether each and every net of the half adder is free of defects or not. So DFT team, we do not check the functionality. We check whether each and every net of the half adder is free of defects or not. So say for example, this is what is our intended design. So this is our half adder. This is our intended design. So where A and B of this half adder, it is actually coming from scan flop. So both are XORed and that is nothing but sum that is going to a scan flop. And then A and B both are ANDed. So A and B both are ANDed. And that is what is nothing but carry. So that is going to another scan flop. So this is what is our intended design, our half adder design. So A XOR B carry is AB. So where A and B are coming from some scan flop and sum and carry it is going to a scan flop. Now suppose during manufacturing, unintentionally during manufacturing, A net of this AND gate has got connected to ground. So unintentionally during manufacturing, A net of this AND gate has got connected to ground. Okay. So this is what will be, these kind of things is what will be checked by the DFT team. Okay, so unintentionally. So this is our intended design. But here in this slide, what I have shown, unintentionally during manufacturing, A net of this AND gate has got connected to ground. So this is what will be checked by the DFT team. So DFT team, we do not check the functionality. We check whether each and every net of the half adder is free of defects or not. So this is our intended design. But suppose during manufacturing, unintentionally during manufacturing, A net of this AND gate has got connected to ground. Okay, unintentionally during manufacturing, A net of this AND gate has got connected to ground. So these kind of things is what will be checked by the DFT team. So DFT team, we do not check the functionality. We check whether each and every net of the half adder is free of defects or not. Okay. So unintentionally during manufacturing, A net of this AND gate has got connected to ground. So this is what will be checked by the DFT team. We do not check the functionality. We check whether each and every net of the half adder is free of manufacturing defects or not. Okay. So now in order to strengthen our understanding more on like what is the difference between a DFT team and a functional verification team, and why do we need both the DFT team as well as a functional verification team, let us try to take up this one more example. So why do we need a DFT team when we have a functional verification team? Okay, so suppose consider a design. So consider a design. In my design, I'm having a 10-bit counter with a counter initialization and a counter observation circuit. So I'm having a design. So in my design, I'm having a 10-bit counter with a counter initialization and a counter observation circuit. So scenario is, suppose the counter is manufactured with a defect. So after counting 999, instead of counting 1000, it incorrectly rolls back to 999. Okay, so after counting 999, instead of counting 1000, it incorrectly rolls back to 999. This is what is the scenario which we are considering. So scenario is, suppose the counter has been manufactured with a defect. Okay, suppose the counter is manufactured with a defect. So that's why after counting 999, instead of counting 1000, it incorrectly rolls back to 999. So now we will try to understand what will happen if only functional verification team exists and what will happen if a DFT team exists. So we'll try to understand what will happen if only functional verification team exists and what will happen if a DFT team exists. So can anyone just tell? So this is our design. Our design is a 10-bit counter with a counter initialization and a counter observation circuit. So scenario is counter is manufactured with a defect. So that's why after counting 999, instead of counting 1000, it incorrectly rolls back to 999. So can anyone tell what will happen if only functional verification team exists? So if only functional verification team exists, then what will happen? The scenario is, suppose the counter is manufactured with a defect. So that's why after counting 999, instead of counting 1000, it incorrectly rolls back to 999. Scenario is, suppose the counter is manufactured with a defect. So that's why after counting 999, instead of counting 1000, it incorrectly rolls back to 999. Okay. So now, if only functional verification team exists, then functional team tests the counter using functional patterns. So in this case, it will take more than 1000 clock pulses to tell that the counter is failing. Can anyone guess? Can anyone guess why in this case it will take more than 1000 clock pulses to tell that the counter is failing? Can anyone guess that?
Ma'am, is it because like in the 999 it goes to 999, and in 1000, no, it will go to either, if you're going with functional verification team, it will go to 1000 clock pulse because it functional verification will be done only before pre-silicon, right?
Yes, correct. So functional verification team, they will be checking the functionality. So functional verification team, I have written here that it will take more than 1000 clock pulses to tell that the counter is failing. The reason is functional verification team, they will be checking the functionality. Functionality means in this case, our design is a 10-bit counter. Our design is a 10-bit counter. So here in this case, so functional verification team, they will be checking the functionality. They will be checking the functionality. So that is, they will check if the counter counts from 0 to 1023. So that is, they will check if the counter counts from 0 to 1023. Checking the functionality means they will check if the counter counts from 0 to 1023. Counts from 0 to 1023. Okay, so functional verification team check the functionality means what does it mean? It means that they will check if the counter counts from 0 to 1023. So the counter is failing at the 1000th pulse. Okay, the counter is failing at the 1000th pulse. The counter is failing at the 1000th pulse. It's failing at the 1000th pulse here. So why is it failing at the 1000th pulse? Can anyone just guess why is the counter failing at the 1000th pulse in this particular case?
there might be some defect in the fourth bit.
Just 1 second, I'll just like open the door and come. Just 1 minute. Yeah, sorry about it. So here in this case, the counter is failing at the 1000th pulse. So why is it failing at the 1000th pulse in this case? It is because at the 1000th pulse only, counter is again counting 999 instead of 1000. Okay, because at the 1000th pulse, that is at the 1000th pulse, at the 1000th pulse only, counter is again counting 999 instead of 1000. Counter is again counting 999 instead of 1000. Okay, so that's why 1000 pulses are required for this. 1000 pulses are required for this. And then some more clock pulses are required for counter initialization and counter observation. So some more clock pulses are required for counter initialization and counter observation. Counter initialization and counter observation. So counter initialization means counter, it has to be brought to the initial state. And counter observation means output of the counter, it has to be taken to some register and the register has to be read. So some more clock pulses are required for counter initialization and counter observation. So that's why we can say that functional verification team, they will require more than 1000 clock pulses to tell that the counter is failing. So functional verification team, they will be testing the counter using functional patterns. So in this case, I have told that it will take more than 1000 clock pulses to tell that the counter is failing. The reason is functional verification team, they will be checking the functionality. So checking the functionality means in this case, it is a 10-bit counter. So that's why they will check if the counter counts from 0 to 1023. So the counter is failing at the 1000th pulse. So because at the 1000th pulse only, counter is again counting 999 instead of 1000. So here we have told, right? So suppose counter is manufactured with a defect. So that's why after counting 999 instead of counting 1000, it incorrectly rolls back to 999. So that is at the 1000th pulse only, counter is again counting 999 instead of 1000. So counter is failing at the 1000th pulse. So 1000 pulses are required. And then some more clock pulses are required for counter initialization and counter observation. So counter initialization means counter, it has to be brought to some initial state, and counter observation means output of the counter, it has to be taken to some register and the register has to be read. Okay. So some more clock pulses are required for counter initialization and counter observation. And then
Ma'am, where will
functional,
this sorry to interrupt, ma'am, where will this functional verification team come in the ASIC flow? Like,
it will be coming in the pre-silicon only, but here I'm just telling that if in case like functional verification team, if they test the chip after manufacturing, what will happen? If DFT team tests the chip after manufacturing, what will happen? And then we will be doing a comparison and we'll try to understand why is a DFT team required.
okay, okay.
Yeah. And then functional verification team, they can only tell if the counter is failing. So functional verification team, they can only tell that the counter is failing. So why? Because they will be checking the functionality. They will be checking the functionality. So which means they will check if the counter counts from 0 to 1023 properly or not. So that is, they will check if the counter counts from 0 to 1023 properly or not. If the counter properly counts from 0 to 1023. The counter counts from 0 to 1023 properly or not. 0 to 1023 properly or not. Okay. So in this case, what is happening after counting 999, instead of incrementing to 1000, it is once again counting 999. So in this case, after counting 999, instead of incrementing to 1000, instead of incrementing to 1000, it is once again counting 999. It is once again counting 999. So the counter is failed. So they can say that counter is failed. Okay. So functional verification team can only tell that the counter is failing. The reason is because they will be checking the functionality. So they will check if the counter counts from 0 to 1023 properly or not. Checking the functionality means in this case it is a 10-bit counter. So they will check if the counter counts from 0 to 1023 properly or not. So in this case, after counting 999, instead of incrementing to 1000, it is once again counting 999. So that's why the counter is failing. So they can only tell that the counter is failing. They are checking the functionality. They will check if the counter counts from 0 to 1023 properly or not. So in this case, after counting 999, instead of counting 1000, it is once again counting 999. So that's the counter is failing. Okay, so this is what will happen when our functional verification team is there. So the scenario which we are considering is, suppose the counter is manufactured with a defect. So after counting 999, instead of counting 1000, it incorrectly rolls back to 999. So what will happen if only functional verification team exists? They will check the counter using functional patterns. So in this case, it will take more than 1000 clock pulses to tell that the counter is failing. The reason is they will be checking the functionality. So functional verification team means they will be checking the functionality. So which means they will check if the counter counts from 0 to 1023. So the counter is failing at the 1000th pulse, because at the 1000th pulse only counter is again counting 999 instead of 1000. So 1000 pulses are required. And then some more clock pulses are required for counter initialization and counter observation. So counter, it has to be brought to some initial state, that is nothing but counter initialization, and counter observation means output of the counter, it has to be, counter initialization means counter, it has to be brought to some initial state, and counter observation means output of the counter, it has to be taken to some register and the register has to be read. So that is why functional verification team, they will take more than 1000 clock pulses to tell that the counter is failing, because they will be checking the functionality. So in this case, they will check if the counter properly counts from 0 to 1023. So counter is failing at the 1000th pulse, because at the 1000th pulse only counter is again counting 999 instead of counting 1000. So 1000 pulses are required for this itself. And some more clock pulses will be required for counter initialization and counter observation. So ultimately, we can say that functional verification team will require more than 1000 clock pulses to tell that the counter is failing. And then functional verification team can only tell that the counter is failing because they will be checking the functionality. They will check if the counter counts from 0 to 1023 properly or not. So in this case, after counting 999 instead of counting 1000, it is once again counting 999. So that's why they can say that the counter is failing. Okay, so functional verification team can only tell that the counter is failing because they will be checking the functionality. So they will check if the counter counts from 0 to 1023 properly or not. So in this case, after 999, instead of incrementing to 1000, it is once again counting 999. So counter is failing. Sorry. So now the same thing we'll try to understand what will happen if a DFT team exists. The same situation we'll try to understand what will happen if a DFT team exists. So same. So the counter, we are having a 10-bit counter with a counter initialization and a counter observation circuit. So scenario is, suppose the counter is manufactured with a defect. So after counting 999, instead of counting 1000, it incorrectly rolls back to 999. So after counting 999, instead of counting 1000, it incorrectly rolls back to 999. So if a DFT team exists, then what will happen? DFT patterns are used to test the chip. Now, DFT team, we will be able to tell that the counter is failing approximately in the range of 100 clock pulses. So DFT team will be able to tell that the counter is failing in approximately in the range of 100 clock pulses. So approximately in the range of 100 clock pulses means somewhere around 80, 90, 100, 120, etc. Okay, so DFT will be able to tell that the counter is failing approximately in the range of 100 clock pulses. So 80, 90, 100, 120, like that, approximately in the range of 100 clock pulses, DFT engineers will be able to tell that the counter is failing. And how are we able to tell that the counter is failing in significantly less number of clock cycles? It is because we will be going for a technique called as scan insertions, because of which we will be easily able to control and observe our circuits. So we will be understanding about the scan insertion technique more in detail when we do the regular course. When we do it, we will be understanding about the scan insertion technique. So at that time, you will be able to understand. So this example, we will once again take it when we do the like our main course. When we do it, we will be once again taking up this example. So at that time, when we do the scan insertion topic, when we understand the need of scan insertion, we will once again be taking up this example. Okay, so we go for scan DFT team, we will be going for scan insertions. Because of that, we will be easily able to control and observe our circuits. So that's why DFT team, we will be able to tell that the counter is failing approximately in the range of 100 clock pulses itself. So approximately in the range of 100 clock pulses means somewhere around 80, 90, 100, 120 like that. Okay, so how DFT team are able to tell that the counter is failing approximately in the range of 100 clock pulses itself? It is because we will be going for a technique called as scan insertions, because of which we will be easily able to control and observe our circuit. Okay, so can anyone just tell, like, functional verification team, how many clock pulses they had required in order to tell that the counter is failing in this particular case? So
More than 1,000.
DFT, yes, correct. DFT implements circuit to check design at pre-silicon level and check it at post design final product. Yes, Karthik. Yes, Kapil, your answer is correct. So DFT, we will be adding these kind of test structures like scan insertion, MBIST insertion, boundary scan insertion. All these test structures will be adding in our design during the pre-silicon stage to facilitate, that is to help detection of manufacturing defects in a chip. So if suppose a particular chip fails after manufacturing, DFT engineers will be able to tell what manufacturing defect has caused the chip to fail. So yes, Kapil, your understanding is correct. Okay.
Ma'am, like I just had
So
one more doubt. The thing is that like in DFT, you told me that it will be only be able to helpful in checking the manufacturing defects of a chip. So like how do we mimic the manufacturing defect? Because it can arrive anyway, right? It can arrive only
so
during
you're
the
asking,
manufacturing process.
are you asking about the fault simulation process where the ATPG tool will be modeling or mimicking the possible failure situations that might occur after manufacturing? Is that fault
Uh,
simulation process which you're asking?
no, ma'am. Like what I'm asking is that um, like in during manufacturing, no, we don't know what kind of defects can arise, right? So what I'm asking is like in the course, no, like how do I know that? Okay, how do we mimic the manufacturing defects? Like, do we mimic the manufacturing defects, or like how do we do that? I'm like that is what I'm asking. Like we
Okay,
don't know
so
the
the
manufacturing
silicon
defects.
debug.
No?
Okay, so the silicon debug part, the practicals of it is not covered in the course. So we will be like, if like it, silicon debug is not a part of our syllabus. So if required, I can do a overview of it, theoretical overview of it. But practicals like silicon debug is not covered in the course. So in our course, we will be covering the scan insertion, scan compression, ATPG pattern generation, simulations, JTAG boundary scan, and MBIST. So these concepts alone we'll be covering it in the course. So silicon
Okay.
debug is not a part of our syllabus. So if required, I can give you a theoretical idea on how silicon debug would happen. So a theoretically, I can give you an overview idea, but practicals of silicon debug is not covered in our course.
Okay, ma'am. Ma'am, the thing is that like what I didn't get is um, like during manufacturing, no, there can be any number of defects, right? Any number of defects, and there can be numerous kinds of defects which can arise, right? So my
Yes,
question was that
correct.
like those defects, how will we mimic those defects in our course? That is what I wanted to ask.
Are you asking
Like
about
say
the fault
suppose
modeling? Are you
uh,
asking about the stuck at fault model, transition delay fault model, those things?
no, ma'am, not that. Okay, okay, I'll ask the question later on, ma'am, so that it'll be helpful for all others, right?
Okay.
Okay.
So yeah, in this case, functional verification team, they will require more than 1,000 clock pulses to tell that the counter is failing. So functional verification team, they will require more than 1,000 clock pulses to tell that the counter is failing. More than 1,000 clock pulses. Okay, so functional verification team, they will require more than 1,000 clock pulses to tell that the counter is failing. And then DFT team. So DFT team, so we will require, as I told, we will require approximately in the range of 100 clock pulses to tell that the counter is failing. So DFT team we will require approximately in the range of 100 clock pulses. So 100 clock pulses. So yeah, DFT team we will be able to tell that the counter is failing approximately in the range of 100 clock pulses. Okay. So DFT will be able to tell that the counter is failing approximately in the range of 100 clock pulses. So functional verification team for the same case they had required more than 1000 clock pulses. Whereas DFT team we require approximately in the range of 100 clock pulses. So if you see, the DFT team we require significantly less number of clock pulses compared to functional verification team. So that's why test time will be less compared to the functional verification team. So DFT team we require significantly less number of clock pulses compared to functional verification team. So that's why test time will be less compared to the functional verification team. So if you see functional verification team, they require more than 1000 clock pulses to tell that the counter is failing. Whereas DFT team, we require approximately in the range of 100 clock pulses to tell that the counter is failing. So if you see, DFT team, we require significantly less number of clock pulses compared to functional verification team, because for the same situation, functional verification team had required more than 1000 clock pulses. Whereas DFT team, we require approximately in the range of 100 clock pulses. So as DFT team, we require significantly less number of clock pulses compared to functional verification team. So test time will be less compared to functional verification team. Okay. So DFT team we require significantly less number of clock pulses compared to functional verification team. So test time will be less compared to functional verification team. And then DFT team will be able to tell that the counter is failing and also tell what manufacturing defect has caused the counter to fail. And how is DFT team able to give this additional detail? How is DFT team able to tell what manufacturing defect has caused the circuit to fail, has caused the counter to fail? So it is because DFT team we will be generating the patterns using ATPG. An ATPG tool does the technique called as fault simulation to generate the test patterns. And what is the fault simulation technique? We will be discussing it in detail. We will be discussing about this fault simulation technique in detail when we do the ATPG topic. So fault simulation is not a straightforward topic. So we will be discussing it in detail during the ATPG topic when we do the main course. Okay, so DFT team will be able to tell that the counter is failing and also tell what manufacturing defect has caused the counter to fail. And how is DFT team able to tell that what manufacturing defect has caused the counter to fail? It is because DFT team we will be generating the patterns using ATPG, and ATPG tool does fault simulation to generate a test pattern. So what is the fault simulation technique? You will be able to understand it when we do the ATPG topic. When we do, you will be able to understand the fault simulation technique. So that is why DFT engineers will be able to tell what manufacturing defect has caused the chip to fail, has caused the counter to fail. Okay. And now conclusion is, with DFT patterns, test time will be less compared to the functional patterns. So DFT will be able to tell what manufacturing defect has caused the chip to fail. This is the conclusion. These are the advantages. So with DFT patterns, test time will be less compared to functional patterns, and DFT will be able to tell what manufacturing defect has caused the chip to fail. So as DFT patterns has these advantages over functional patterns, DFT patterns will be used to test the chip after manufacturing. Some functional patterns also will be used to test the chip after manufacturing, but majority DFT patterns will be used to test the chip after manufacturing. Okay, so with DFT patterns, test time will be less compared to functional patterns. And DFT will be able to tell what manufacturing defect has caused the chip to fail. So this is what is the conclusion. So with DFT patterns, test time will be less compared to functional patterns. And with DFT patterns, we will be able to tell what manufacturing defect has caused the chip to fail. Okay. So as DFT patterns has these advantages over functional patterns, DFT patterns will be used to test the chip after manufacturing. So some functional patterns will also be used to test the chip after manufacturing. But majority DFT patterns will be used to test the chip after manufacturing. Okay. And then, can anyone just tell, if DFT patterns are used to test the chip after manufacturing, why do we need a functional verification team? So can anyone just try to guess this answer? Okay, let me just take up some questions which is actually there in the chat box. So is there any possibilities that DFT circuits can have manufacturing defects? So DFT circuits means the scan chains, Q to SI path, the EDT logic, those things, whether it can have a manufacturing defect? Yes, there is a possibility that there can be manufacturing defects in the this one DFT circuits also. So our tool will be writing a set of chain patterns to test the Q to SI path. Yeah, so we will be discussing it in the course. Okay, so yes, there can be some manufacturing defects in the scan chains Q to SI path, or else in the compression logic, in the BIST logic and all. Yes, there is a chance that you can have a manufacturing defect, and we will also be discussing how those things can also be tested. Will be covered in our course. Okay. Can you said that the technique scan insertion will be discussed later, but now can it be explained little bit how this particular problem can be solved? Shilpa, like in order to understand how you need to understand what is a scan cell, what is a scan chain, how a scan chain operates, and then only you will be able to understand like what is it, how in this particular case we will be able to tell that the counter is failing approximately in the range of 100 clock pulses. So in order to explain that, in order to understand all those things, like it might take around 3 hours to explain. So that's why we will be doing it in our course. So here in our regular course material. So first we will be discussing all these points. So one second, just one second. Yeah, so first we have to understand all these points, like what is a scan cell? Okay, so like what is a scan cell? And then what is a normal flop, what is a scan flop, and what is a scan chain, why are we actually forming a scan chain, and how does the scan chain operate? So all these things you have to understand, how does a scan chain operate. And then we will yeah, after understanding all these points only, we will be once again taking up this counter example, and later only after you have understood all those points, you will be able to see. So in this case, we will be explaining it through the waveforms like this. We will be explaining it, and we will be showing you how you will be able to tell that the counter is failing approximately in the range of 100 clock pulses itself. In our course, we will be explaining that. Okay. But in order to understand what is written here, in order to understand, you need to understand like what is a scan cell, what is a scan chain, how does it operate. So only then you will be able to understand how in that counter example you will be able to tell that the counter is failing approximately in the range of 100 clock pulses itself. Okay, so which will actually take around 3 hours to explain. So we will be doing the explanations in detail in the main course. When we do, you will be able to understand those explanations. Okay. For now, you can just remember that we will be going for scan insertions. Because of that, we will be easily able to control and observe our circuit. So we are able to tell that the counter is failing approximately in the range of 100 clock pulses itself. Okay. So as of now, you just remember this point. Later, when we come to the advanced part of the training, when we do the course, you will be able to understand it. Okay. How you will be able to understand. So yeah. So as I told here, DFT patterns were having those advantages. So with DFT patterns, test time will be less compared to functional patterns, and DFT will be able to tell what manufacturing defect has caused the chip to fail. So as DFT patterns has these advantages over functional patterns, DFT patterns will be used to test the chip after manufacturing. Some functional patterns also will be used to test the chip after manufacturing, but majority DFT patterns will be used to test the chip after manufacturing. So now, can anyone just tell, if DFT patterns are used to test the chip after manufacturing, why do we need a functional verification team? So can anyone just guess? If DFT patterns are used to test the chip after manufacturing, why do we need a functional verification team? So to ensure the functionality of the chip, functional verification is needed before DFT. Yeah, since after manufacturing, if the functionality is not okay, the chip is wasted already. Yes, Shilpa, your answer is correct. So yes, whatever Shilpa has told is correct. And let's try to take up an example, and let's try to understand. Suppose there is someone has written this half-added design, a simple design, a half-added design I'm just considering. So sum is written as A plus B and carry is written as AB. So whether this is correct, so sum is written as A plus B and carry is written as AB for a half added. So whether this is correct, can anyone tell whether this is correct? No, this is not correct. Yes, Shilpa, your answer is correct. So this is a functional bug. So sum should have been A XOR B. Yes, Kapil, your answer is also correct. So sum should have been A XOR B. But someone mistakenly they have written sum is equal to A plus B. So this is the functional bug. Now this is for time being consider that there is no functional verification team. Okay, for time being consider that there is no functional verification team. So directly the design has got synthesized. So this is a wrong design has got synthesized. And this design is given to the DFT team. So DFT team, we will be generating patterns just to check whether there are any manufacturing defects in each and every net of this design. So DFT team, we will be generating patterns just to check whether there are any manufacturing defects in each and every net of this design. Now the chip has been manufactured. So DFT patterns are applied onto the chip. And then the output of the chip is compared with the expected output. So chip has been manufactured. So DFT patterns are applied onto the chip. And then the output of the chip is compared with the expected output. Now output of the chip is equal to the expected output, which means that there are no manufacturing defects. But whether this circuit will function like a half adder. So there are no manufacturing defects in this case. Whether the circuit will function like a half adder or not in this particular situation. Yes, no, it will not function. And why will it not function? Any guesses? Because yes, the functionality was not correct. Yes, Shilpa, Kapil and Chetan, all your answers are correct. So whether the circuit will function like a half adder? No, because even though there are no manufacturing defects, the circuit will not function like a half adder. Okay, even though there are no manufacturing defects, the circuit will not function like a half adder. Why? The design itself is wrong. Okay, even though there are no manufacturing defects, the circuit will not function like a half adder. Why? The design itself is wrong. Okay, at the design stage itself, it was wrong. Sum was written as A plus B. The design itself was wrong. So that is what is the significance of the functional verification team. They will be validating the functionality. So whatever is written here, whether this is correct or not. So sum is written as A plus B, carry is written as AB. So whatever is written here, whether this is correct or not. So that is what will be validated by the functional verification team. Okay, so yeah, they will be checking the functionality over here. Okay, so whatever is written, whether this is correct or not. So this is what will be checked by the functional verification team. So this is the significance of functional verification team. They will be validating the functionality. So whatever is written, whether this is correct or not. So that is what will be validated by the functional verification team. Okay. So now you would have got an idea on what is the difference between a DFT team and a functional verification team, and why do we need both the DFT team as well as a functional verification team. Okay, so like why do we need a DFT team? Why do we need a functional verification team? And what are the differences between the roles of a DFT engineer and a functional verification engineer? So you will be able, you would have got an idea about it. Okay, and yeah. Chetan, you had asked a question, right? Like how we can find out at which particular node a manufacturing defect would be there. So like here in this case, DFT team, we will be generating patterns using ATPG. So ATPG tool does fault simulation to generate the test pattern. So if because ATPG tool uses this fault simulation technique to generate a test patterns. If in case a particular pattern fails, our tool will be able to tell the possible manufacturing defects that could have occurred with the help of the scan diagnosis technique. And scan diagnosis is what is silicon debug. So it is not covered in our syllabus, but I will try to give you an overview on what would happen in the silicon debug, what would happen and how is the scan diagnosis tool able to give the possible manufacturing defects that could have occurred. So ATPG tool does fault simulation technique in order to generate the test patterns. So as ATPG tool does fault simulation to generate the test patterns only, if in case a particular pattern fails, diagnosis tool will be able to give the possible manufacturing defects that could have occurred. And I will try to give you a theoretical overview. So it's not covered in our course, but I'll try to give you a theoretical overview when we do the course. I will try to give you a theoretical overview on how the diagnostic tool will be able to tell the possible manufacturing defect that could have occurred. Okay, so what does the diagnostic tool do internally in order to find out what manufacturing defect has caused the circuit to fail. Okay, so in order to do that, how does the diagnostic tool able to do it? So I will try to give you a theoretical overview when we do the main course. So this is what is the answer to your question. So ATPG tool does fault simulation to generate the test pattern. Fault simulation technique, we will be discussing it in our course in detail. So as ATPG tool does fault simulation to generate the test pattern only, if in case a particular pattern fails, diagnosis tool will be able to tell possible manufacturing defects that could have occurred. So that also, how is the diagnostic tool able to give that detail? I will give you an idea about it in the course. Okay, when we do the course, I will give you a theoretical idea on silicon debug part, that is nothing but scan diagnosis part. How does the scan diagnosis tool able to give the possible manufacturing defects that could have occurred? Okay, so okay. And now let's try to understand what will happen during this testing. So testing is also done after manufacturing. As you know, testing is done after manufacturing. The ASIC flow slide, we had packaging and testing slide, right? So testing is actually done after manufacturing. Okay. So testing is a process of determining whether a device is good or not. So in our case, whether a chip is good or not, whether there are any manufacturing defects or not. So in this case, it is actually to check if our chip is good or not. So testing is a process of determining whether a device is good or not. So it is actually to check if our chip is good or not. So it is to check if our chip is good or not. Good or not. Okay, that is to check whether there are any manufacturing defects or not. That is to check whether there are any manufacturing defects or not. Whether there are any manufacturing defects or not. Manufacturing defects or not. So testing is a process of determining whether a device is good or not. So that is to check if our chip is good or not, to check whether there are any manufacturing defects or not. So testing is actually done after manufacturing. Okay. So testing is a process of determining whether a device is good or not, to check if our chip is good or not, to check whether there are any manufacturing defects or not. So testing includes test pattern generation, application, and output evaluation. So testing includes test pattern generation, application, and output evaluation. So these test patterns, it will be generated by the DFT engineer. Before manufacturing itself, will be generating the test patterns. Okay, and it will be consisting of input sequence and expected output. So now what will happen? This input sequence will be applied onto the chip. So the input sequence will be applied onto the chip, and then the output of the chip, it will be compared with the expected output. So output of the chip, it will be compared with the expected output. So output of the chip, if it is equal to expected output, it means that the chip is good, there are no manufacturing defects. And output of the chip, if it is not equal to the expected output, it means that the chip has failed, there are some manufacturing defects in the chip. So if in case a particular chip fails, DFT engineers will be able to tell what manufacturing defect has caused the chip to fail. Okay, so yeah. So these test patterns are there, right? These test patterns, it will be generated by the DFT engineer. Before manufacturing itself, we will be generating the test patterns. So it will be consisting of input sequence and expected output. So the input sequence, it will be applied onto the chip. Input sequence will be applied onto the chip, and then the output of the chip will be compared with the expected output. So output of the chip, if it is equal to the expected output, it means that the chip is good, there are no manufacturing defects. And output of the chip, if it is not equal to the expected output, it means that the chip has failed, there are some manufacturing defects in the chip. So if a particular chip fails, DFT engineers will be able to tell what manufacturing defect has caused the chip to fail. So if suppose a particular chip fails, DFT engineers will be able to tell what manufacturing defect has caused the chip to fail. Okay. So, and now what are called as these manufacturing defects? Manufacturing defects means they are the defects that are caused due to process variations and random imperfections. So the defects that are caused due to process variations and random imperfections. So process variations means slight variation in the transistor channel length. So slight variation in the transistor channel length, okay, slight variation in the transistor channel length, and then metal interconnect width and thickness. So metal interconnect width and thickness, okay. So all these things can impact the logical and timing performance. So all these things can actually impact the logical and timing performance. Logical and timing performance. So process variation, so slight variation in the transistor channel length, metal interconnect width and thickness. So all those things, it can actually impact the logical and timing performance. And random imperfections means it can result in unintentional shorts, opens, all those things are only random imperfections. So it can result in unintentional shorts, opens, etc. Okay, so that is what. So defects that are caused due to process variation and random imperfection. So process variation means slight variation in the transistor channel length, metal interconnect width and thickness. All those things can impact the logical and timing performance. And random imperfections means it can result in unintentional shorts, unintentional opens. So that is what is called as random imperfections. And the flow of DFT means we will be adding up extra logic. We'll be adding up extra logic like scan insertion, MBIST insertion, boundary scan insertion. Like that, we will be adding up extra logic. And then we will be generating the patterns. So the input data and expected output. So we will be doing the pattern generation, input data and expected output. And then we will be doing the simulation validation. Okay. So before delivering the patterns that are generated during ATPG to test the chip after manufacturing, we need to validate once whether proper patterns are generated or not. So that validation is what is called as simulations. Okay, so before delivering the test patterns generated during ATPG to test the chip after manufacturing, we need to validate once whether proper patterns are generated or not. So that validation is what is called as simulations. Okay, so we'll be doing the simulation validation all this. And this is what is our course outline. So in our course outline, we will be covering what is scan insertions, scan compressions, on-chip clock controller OCC, automatic test pattern generation ATPG, simulations. So simulations, as of now, only no timing simulation is covered in our course. So in simulations, as of now, only no timing simulations. Only no timing simulation is covered. Only no timing simulation is covered. Okay, so simulations, as of now, only no timing simulation is covered in our course. Okay, in our DFT course, as of now, only no timing simulation is covered. And then we will be covering the JTAG. So JTAG full form is Joint Test Action Group. So it's an IEEE 1149.1 standard. It is an IEEE 1149.1 standard. We will also be covering IJTAG. We will also be covering IJTAG, which is an IEEE 1687 standard, which is an IEEE 1687 standard. Okay, so JTAG full form is Joint Test Action Group. So it's an IEEE 1149.1 standard. And we will also be covering IJTAG, which is nothing but IEEE 1687 standard. And then we will also be covering MBIST, Memory Built-in Self-Test. MBIST we will be covering, and we'll be covering the boundary scan. And boundary scan we will be covering only theoretically. We'll be covering only theoretically. So we don't have the license to do the boundary scan. So boundary scan we'll be doing only theoretically. Okay. So yeah, this is what is our course outline. So now let me just try to give you an idea on what are all the things will be covered in each topic. What are all the things will be covered? Let me just try to give you an idea on it. So the first topic here is scan insertions. So topic one is scan insertions. Okay. So in scan insertions, internally, what are all the topics we will be covering is, we will be covering what is a scan cell. So scan cell functionality. scan cell functionality, and we will be covering the scan chain functionality, and we will also be covering the need of scan insertions. So need of scan insertions. So as I told, we will be, after understanding what is a scan cell, its functionality, after understanding the scan chain and then its functionality, we will be revisiting the counter example which I told today in the demo session. And then we will be understanding how in that particular counter example you are able to tell that the counter is failing approximately in the range of 100 clock pulses itself. So you'll also be understanding the need of scan insertion. While understanding the need of scan insertion topic, we will once again take up that counter example, and we'll try to understand how DFT team will be able to tell that the counter is failing approximately in the range of 100 clock pulses itself. So how you will be able to, we will be explaining it at that time. So today I wasn't able to explain because like in order to understand that, you need to understand like scan cell functionality, scan chain functionality, and then only you'll be able to understand that point. Okay, so that's why I didn't tell today, but we will be covering it in our course. So we will show you while doing this need of scan insertion topic, we will show you with the help by mathematically doing the, as I showed there, right? I had written in the previous batch. Mathematically, we will be doing some calculations, and I will be showing you how if you go for scan insertion, you will be able to tell that the counter is failing approximately in the range of 100 clock pulses itself. Okay. And then we will be discussing about scan DRCs. So we will be discussing about scan DRCs. So DRC stands for design rule checks. So DRC stands for design rule checks. Okay. So like when we do this topic, we will be able to understand what is scan DRC. What are scan DRCs? Why scan? What are scan design rule checks? What is it basically? Why it is required? We will understand. And there will be various scan DRCs like clock controllability DRC. Okay, there will be various scan DRCs like clock controllability DRC, and then set reset controllability DRC, set reset controllability DRC. Okay, and then feedback loop DRC, feedback loop DRC, and then potential raise DRC, potential raise DRC, and then X source DRC, and then bus contention. So these are all the various scan DRCs. So scan DRCs means design rule checks. So what is basically called as scan DRC? So scan DRCs means what they will understand, and we'll be understanding about the various scan DRCs like clock controllability DRC. What is clock controllability DRC? So in which kind of situations it will be violated and how we can resolve it, how we can overcome the violation, like that. Same way for all the DRC, set reset controllability DRC, feedback loop DRC, potential raise DRC, X source DRC, bus contention DRC. These are all the various scan DRCs. We will understand what is each rule, when it will be violated, and what can be done, how to resolve it, if in case it gets violated. So we will be covering it in our course. And then we will be understanding something called as scan chain balancing. We'll be understanding scan chain balancing. Okay, so scan chain balancing we will be understanding. And here also we will understand what is scan chain balancing. Okay, what is scan chain balancing? Why do we need scan chain balancing? And how we can achieve scan chain balancing. So what is scan chain balancing? Why do we need to go for balanced scan chains? And how to achieve scan chain balancing? So how to achieve scan chain balancing? We will be discussing about edge mixing and domain mixing technique. We'll be discussing about the edge mixing and domain mixing technique. Edge mixing and domain mixing technique. So we will try to understand what is edge mixing, what is domain mixing technique, how by going for edge mixing and domain mixing technique you are achieving balanced scan chains. So all these things we will understand. And later we have understood that by going for this edge mixing and domain mixing technique, you will be able to achieve balanced scan chains. And the reason why you have to achieve balanced scan chain also, we will be understanding it in our course. So what is scan chain balancing and why do we need to achieve scan chain balancing also, we'll be discussing it in our course. So we'll be going for that edge mixing and domain mixing technique to achieve scan chain balancing. Now, if you go for edge mixing and domain mixing, it will again introduce some problems. So what problems edge mixing and domain mixing will introduce and what has to be its solution, we will be discussing. So problems in edge mixing and domain mixing, problems in edge mixing and domain mixing, and then its solutions, we will be understanding. Okay. So what are the problems in edge mixing and domain mixing technique and what are its solutions, we will be understanding. Okay, so what problems, if you go for this edge mixing and domain mixing technique, again, what problems it will introduce and what are its solutions, we will try to understand. These are the topics, these are the subtopics which we will be covering it as a part of our scan insertion topic. Okay, so as of now, I'm talking about the theory part. After covering the theory part topic course content, I will tell you what all the topics we'll be covering it in our lab part also. Okay, so topic 2 is scan compression. So topic 2 is scan compression. Okay, so scan compression is nothing but EDT insertion. So scan compression is also called as EDT insertion. So again, here also we will try to understand what is scan compression, why do we need to go for scan compression, okay, what is the need of scan compression, and then there will be a particular quantity called as compression ratio. There will be a particular quantity called as sorry, one second. So there will be a particular quantity called as compression ratio. Okay, so compression ratio. So compression ratio, we will be understanding what is compression ratio. What is this quantity compression ratio, we'll understand. And we will also be able to understand the merits and demerits of high and low compression ratio. We will be able to understand the merits and demerits. Merits and demerits of high and low compression ratio. High and low compression ratio. So all these things we will be able to understand. So what is compression ratio? Sorry, what is scan compression? Why do we need to go for scan compression? And compression ratio. Compression ratio, there will be a quantity called as compression ratio. So what is that what is that quantity, compression ratio quantity? And what are the merits and demerits of having high and low compression ratio? We will be understanding. And in order to achieve scan compression, if you are using Mentor graphics tools, we will be adding up a logic called as EDT logic. So the full form of EDT is embedded deterministic test. So the full form of EDT is embedded deterministic test. Okay. So we will be understanding about this EDT logic. We will be understanding about the EDT logic. And we will also be understanding, like in EDT logic, you will be having various components inside EDT logic. Like you have the decompressor. Okay, so you will be having the decompressor. Okay, one second. Let me just write that here. Okay, so we'll be understanding about the EDT logic. So in the EDT logic, we will be understanding about the various components of the EDT logic. So one is the decompressor. Okay, and then compressor block, compressor, and then controller, and then the bypass logic. So these are the 4 components of EDT logic. So in EDT logic, we'll be having the decompressor, then compressor, controller, and then bypass logic. So these are the 4 components of EDT logic. So in order to achieve scan compression, if you're using Mentor graphics tools, then we will be adding up a EDT logic. So the full form of EDT is embedded deterministic test. So we'll be having, there will be 4 components in the EDT logic like decompressor, compressor, controller, and bypass logic. So we will try to understand about each and every component, like decompressor component means what is its structure, what is the functionality, and what role it plays in scan compression. Same way compressor, same way controller, same way bypass logic, all those things we will try to understand its structure, its functionality, and what role it plays in scan compression. Okay. And then we will try to understand about the pipeline flops in the compressor logic and lockup cells in EDT. So all those things we will try to understand. So pipeline flops and compressor logic, and then lockup cells in EDT, lockup cells in EDT. So all those things we will try to understand. So pipeline flops in the compressor logic, lockup cells in EDT. So all those things we will be understanding. Okay. And then the next topic which we will be covering is the ATPG topic. So ATPG is a very vast topic. So let me just tell you what are all the points we will be covering it in the ATPG topic. So we'll understand what is ATPG, and then we'll also understand about the fault simulation technique. Okay, we will be understanding about the fault simulation technique, and we will be covering the fault models. So in fault models, we will be covering the stuck at fault model, and then transition delay fault model, and then the path delay fault model, and then the IDDQ fault model. So transition delay fault model and path delay fault model, so we will be calling it as at-speed test. We'll be calling it as the at-speed test. So these fault models we will be covering. So stuck at fault model, transition delay fault model, path delay fault model, IDDQ fault model. So transition delay fault model and path delay fault model, we'll be calling it as the at-speed test. And fault classes. So fault classes, like faults, they will be broadly classified into two classes. So one is testable and the other one is untestable. Under untestable, they will be further subclassified as unused, tied, blocked, and then redundant. So under untestable, they will be further classified as unused, tied, blocked, and redundant. And under testable, they will be classified as detected, possible detected, ATPG untestable, and then undetected. Okay. So these are the fault classes. So faults, they are broadly classified into testable and untestable. So under untestable, we have unused, tied, blocked, and redundant. And under testable, we have detected, possible detected, ATPG untestable, and undetected. Okay. And then we will be having, like, we will also be understanding about fault dominance, fault equivalence, and fault collapse. So fault dominance, fault equivalence, and then fault collapse. Okay. And then we will also be understanding like fault aliasing. We'll also be understanding fault aliasing. And we'll be understanding like what is coverage, what is fault coverage, what is test coverage, all those things we'll understand. Coverage, and then what is the fault coverage, what is the test coverage. So all those things we will understand. We'll be understanding about test point insertions. Okay. We will understand about pattern classification. How are the patterns classified? Serial pattern, parallel pattern, chain pattern, capture pattern, Verilog style, wiggle. So like that pattern classifications, all those things we will understand. Okay. And then we will be understanding about OCC architecture, on-chip clock controller, OCC architecture we will understand. And then we will also be understanding about the placement of OCC. We will also be understanding about the placement of OCC. So all those things we will be understanding. Okay. So under ATPG, we will be understanding what is ATPG, what is fault simulation. We'll be understanding the various fault models like StructCAD, PDF, PDF, IDDQ, fault classes, various fault classes you have, testable and untestable, they are broadly classified. So under untestable, you have unused, tight, blocked, redundant. Under testable, you have detected, possible, detected, ATPG, untestable, undetected. So we'll be understanding about each fault class. We will be understanding what is each fault class and their subclass we'll be understanding. And then we'll also try to understand what is fault dominance equivalence and what is fault collapsing. We will understand what is fault aliasing, what is coverage, what is fault coverage, and what is test coverage. We'll understand what are test point insertions, okay, how patterns are classified, what is the on-chip clock controller, OCC architecture, and how the placement of OCC will happen, where to place the OCC, all those things. So all these topics we will be discussing it in our course. Okay. And then topic 4 will be simulations. So under simulations, you will be understanding, like, again, what is simulations? Why do we need to go for simulations? Okay. And then what is the flow of simulations? Okay. So what are serial simulations and parallel simulations? What are serial simulations and parallel simulations? Serial and parallel simulations. Okay. So like, what is a simulation mismatch debug procedure? So if in case your simulation fails, what is the procedure to debug it? Okay. So simulation mismatch debug. Simulation mismatch debug procedure. So all those things. So we'll be understanding what is simulation, why do we need to go for simulation, what is the flow of simulation, what are serial and parallel simulation. So if in case your simulation fails, how we can do the debug, and some extra topics which are not part of our syllabus. So that also I will be covering, like scenarios that can cause, scenarios which can cause serial simulation to fail, but parallel simulation to pass. Okay, so serial simulation fail, parallel simulation to pass, and which scenarios can cause serial simulation to pass and parallel simulation to fail. Serial simulation to pass and parallel simulation to fail. Okay, so scenarios which can cause serial simulation fail, parallel simulation pass, and serial simulation pass and parallel simulation fail. Okay, so we'll be understanding that. And then we will be understanding about the topic 5A is nothing but JTAG. So JTAG is nothing but an IEEE 1149.1 standard. So JTAG is IEEE 1149.1 standard. Okay, so topic 5, A and B we will consider. Topic 5A is JTAG, which is an IEEE 1149.1 standard. So we will be understanding the need of JTAG. We will be understanding the JTAG TAP architecture, JTAG TAP architecture. Okay, and then we will be understanding about the JTAG controller. So JTAG controller will be a 16-state FSM. So JTAG controller will be a 16-state FSM. So we'll be understanding about that. Okay, so we'll be understanding JTAG. JTAG is nothing but IEEE 1149.1 standard. So we'll be understanding what is the need of JTAG, the JTAG TAP architecture. So the JTAG controller, which is nothing but a 16-state FSM. And we will also be understanding about IJTAG. IJTAG, which is an IEEE 1687 standard. Okay, so in IJTAG, we will be understanding again, the architecture of IJTAG also we will understand. Okay, JTAG is IEEE 1149.1 standard. IJTAG is IEEE 1687 standard. So again, in IJTAG, we'll be understanding the architecture And then we will be understanding the comparison between JTAG and IJTAG. So comparison between JTAG and IJTAG. Okay. So what are the advantages of IJTAG? What are the advantages of IJTAG? So these things we will understand. So IJTAG is IEEE 1687 standard. So we will be understanding what is the architecture of it. What is the comparison between JTAG and IJTAG? What are the advantages of IJTAG? So all these things we will understand. So we'll be understanding the architecture. We will be we'll be doing a comparison between JTAG and IJTAG, and we will also see the advantages of IJTAG. All these things we will be discussing in the course. And then topic 5B. So topic 5B is nothing but boundary scan. So topic 5B is nothing but boundary scan. So boundary scan, we also call it as B scan. Boundary scan. So we also call it as B scan. Okay. So we will understand what is boundary scan, what is the need of boundary scan, what is the structure of boundary scan cell. So boundary scan cell structure. And then what are the modes of operation of boundary scan cell? Modes of operation of boundary scan cell. And then what are X-test sample preload and bypass instructions? X-test sample preload and then bypass instructions. So all these things we will understand. So topic 5 is nothing but boundary scan. So what is boundary scan? What is the need of boundary scan? What is the structure of boundary scan cell? What are the modes of operation of boundary scan cell? What is X-test sample preload and bypass instruction? All these things we will understand. And same way topic 6. So topic 6, we will understand about MBIST. So the full form of MBIST is memory built-in self-test. So that is what is the full form of MBIST. So full form of MBIST is memory built-in self-test. So we will be understanding, first we will be understanding the basics of memories. We'll be understanding about the basics of memories. And then we will be understanding about the memory fault models. We will be understanding about the memory fault models. So like what is the stuck-at fault model, transition fault model, address decoder fault, coupling fault. So all those things we will understand. We'll understand about the memory fault models like stuck-at fault, transition fault, address decoder fault, coupling fault. All these fault models we will understand. Okay. And then memories, they are actually tested using generalized algorithms. So memories, they are actually tested using generalized algorithms. Memories are tested using generalized algorithms. You see, generalized algorithms. Okay, so memories are tested using generalized algorithms. So there will be various generalized algorithms like 0-1 algorithm and then checkerboard algorithm, and then MATS. Then we have MATS plus, and then we have MATS plus plus, and then we will be having March X, and then March C. Okay, so all these things will be there. So memories are tested using generalized algorithm. So we will be having various algorithms like 0-1 algorithm, checkerboard algorithm, MATS algorithm, MATS plus, March X, March C. Okay, so for each algorithm, we will be understanding what is the sequence and then which algorithm will be able to cover which faults in memories. So which algorithm will be able to cover which faults in memories. Okay, so which faults in memories we will understand, and why memories are tested using generalized algorithm also we will understand. Okay, and then we will be understanding about the Tessent MBIST architecture. We will be understanding about Tessent MBIST. So in Tessent MBIST, we will be understanding the Tessent MBIST implementation and architecture. So we'll be understanding about the MBIST implementation and architecture. So the MBIST operation protocol, the MBIST operation protocol. Okay, so we will be understanding about the BIST setup signal. So we'll be understanding about the BIST setup signal, and then we'll be understanding about the MBIST PG enable signal, MBIST PG enable signal, and then we will be understanding about the go bit, about the done bit. So all these things we'll be understanding. So in the MBIST operation protocol, we'll be understanding about the BIST setup signal, MBIST PG enable signal, the go bit, the done bit, and then we will be understanding about the concept of group and concept of step. And when we do the course, when we do about this MBIST implementation and this architecture, you will be able to understand why is it called as built-in self-test. MBIST stands for memory built-in self-test. So when we do this topic, MBIST implementation and architecture, you will be able to understand why is it called as built-in self-test. So these are all the topics which we will be covering it in our theory course content. And let me just quickly take you through the lab course content also. So our DFT labs, we will be having basically 4 levels of projects. So level 1 and level 2, they are simple labs. Level 3 and level 4 projects, they are actually designs with higher complexity. So it can be projected as a project work in your resume. Level 3 and level 4 projects, you can use it as a project work in your resume. Okay. So like level 1 projects, in level 1 projects, what we will be doing is we will be performing scan insertions. Okay, on 11 simple designs, we will be performing scan insertion. So flop count, it will be only of 100 or 200, in that range it will be there. Okay, as I told, level 1 and level 2 projects are simple labs, complexity will be less. And what are the things we will be learning it in the level 1 projects is, we will be understanding the scan insertion and then its need, and we will be understanding the flow of scan insertion in Tessent tool. So say for example, you want to perform scan insertion using Tessent tools, you will be having a set of steps or a procedure which you have to follow. Like you will be having various phases, setup phase, analysis phase, insertion phase. So what has to be done in each phase? So all these things we will understand. Okay. And then we will be understanding about the various scan DRCs. Okay. So as I told, we will be having various scan DRC rules we will be having. So design rule checks, various scan DRCs we will be having. So we will be getting some rule violations. So DRC rule violations you will be having. Okay. And what we will be doing is we will be analyzing the scan DRC violations in the schematic. So each and every rule, why it is getting violated, we will be analyzing it in our schematic. So tool schematic will be there. So we will be analyzing there. Okay. And then we will be understanding about all these violations. We will be getting all these violations in the scan. In the labs, we will be getting all these violations. So clock controllability and set reset controllability, DRC violation, which is nothing but S1 and S2 violation in Tessent tools. Same way, clock data race DRC, its code is C6 violation in Tessent tool. Same way, bus contention, so its code will be E10 in Tessent tool. Same way, C3 violation, pre-existing scan chain violation, the S6 violation. So all these DRC violations, we will be getting it in our labs. We will be analyzing these DRC violations in this tool schematic. We will be analyzing all these DRC violations in the tool schematic. Okay. And then you will be having various methods with which you can resolve the DRC violation. So first method with which you can resolve the DRC violation is nothing but the manual editing of netlist method. Or else you can make use of Tessent commands like create instance, delete connection, create connection. So you can make use of these commands to fix the DRC violations. Or there is an auto fix method where the tool itself will fix the DRC violations. So all the 3 methods with which we will be fixing the DRC violation, we'll be fixing the DRC violation using all the 3 methods. Okay. And we will also be doing a comparison between each method. Okay. Each method we will be comparing which one is more preferred and why it is more preferred. We will be doing a comparison of this one. And we will also try to achieve balanced scan change by going for edge mixing and domain mixing techniques. We will be adding up some commands and we will be implementing the edge mixing and domain mixing techniques. And we will also be going for lockup insertions whenever we have edge mixing and domain mixing. So what are lockups and all, you'll be able to understand during the course. So whenever we go for edge mixing and domain mixing, we'll be doing the lockups insertion. So what are lockups, why it is inserted, and how to insert it, all those things we'll be discussing it in the course. And various reports and outputs of scan insertions will be generated. So these are the various reports and outputs of scan insertion. So we'll be understanding about each and every report. So what is each report and what are the contents of each and every report and output of scan insertion, where it is actually used, all those things we will be understanding. Okay, where we will be using the outputs of scan, where it is used, what are the contents of each file. Scan cell report means what are its contents. Suppose test proc file means what are its contents. Like that, each and every file contents we will understand. And whatever scan change we have inserted, we will be tracing it in the schematic. So after we have performed the scan insertion, we will trace the logic what we have inserted in the schematic. Okay. And then level 2 projects. Level 2 projects is actually to perform scan compression. In level 2 projects, we will be performing scan compression, which is nothing but EDT insertion, and then ATPG and simulations for the same 11 test cases we'll be performing. So scan compression, that is nothing but EDT insertion, ATPG and simulation for the same 11 test cases we will be performing. And for each and every lab, so say for example, scan compression means we will be understanding like the flow of EDT insertions. So if you are making use of Tessent tools, if you want to add up a EDT logic means there will be a flow, there will be a procedure which you have to follow. So we will be understanding that procedure. What is the procedure which you have to follow in order to do the EDT insertions? So that is nothing but the flow of EDT insertion. And we'll be understanding the number of internal chains and external channels, so how to decide it. And we will be understanding about the merits and demerits of high and low compression ratio. We will be understanding, we'll be inserting the EDT architecture. All these components we will be understanding. Okay, we will be understanding and we will also be adding it into our design. So whatever EDT logic we have inserted, we will trace the EDT hardware in the schematic. Okay, whatever EDT files, EDT logic has been inserted, we will trace it in the schematic. We will also do the pipeline flops insertion in the compressor block. So all those things we will be understanding in the EDT labs. So when we do the labs, you will be able to understand what each step is. Now I'm just telling what all the things will be covered. So you'll be able to understand what each step means when we do the this one. What is it? When we do the labs. Okay. And then ATPG, again, flow of ATPG. So if you want to do pattern generation, test pattern generation using Tessent tools, there will be a flow. There will be a flow or a procedure which you have to follow. So we will be understanding that procedure. And in our labs, we will be generating test patterns for stuck at transition delay and IDDQ fault model. Path delay fault model is only covered theoretically. In labs, we will be covering stuck at transition delay fault model and IDDQ fault model. We will be covering the pattern generation practicals of it. And we'll be doing the pattern generation with EDT and also bypass pattern generation we will be doing. Okay, bypass pattern generation means pattern generated after bypassing the EDT logic. So why do we need to do the bypass pattern generation, and what is the difference between EDT pattern and bypass pattern? Why different patterns are required? All those things also we will understand. And this complete fault classes understanding is very much required in order to work on coverage analysis and coverage improvement. This entire fault classes understanding will be required in order to work on this coverage analysis and coverage improvement. So all these cases, it can actually, these are some of the reasons why you will be getting coverage dropped in our labs. And these are some of the techniques with which we can actually improve the coverage. So these are some of the techniques which we will be using in our labs to improve the coverage. Okay, and we will also be doing the test point insertion, where in Tessent we have an automatic flow. We also write tickle scripts to do the test point insertion. We will be working on ATPG DRCs. We will be understanding about the chain and capture patterns. So all these things we'll be understanding in our class. And simulations, yes, whatever I told, simulations will be done by practicals of simulation will be done by, sorry, theoretical concept of simulation will be done by practically demonstrating in the lab. So whatever I told earlier, the same things would be given here also. Simulation and its need. So we'll be performing simulation using QuestaSim tool. We'll be working on serial and parallel simulation. If in case our simulation fails, how we can do the debug. So all these things we'll be discussing it as a part of our simulation course. And then next, coming to the level 3 projects. In level 3 projects, we are going to do the hierarchical scan. So in level 3 projects, we have a hierarchical scan design with a parent core, core B, and multiple child cores, core A's, and the flop count will be around 4K. So level 3 projects flop count will be around 4K. Level 4 projects flop count will be around 44K. So that's why level 3 and level 4 projects are designs with higher complexities, which can be used as a project work in your resume. So we will be performing all these things in the level 3 projects like MBIST insertion, scan chain stitching, DRC cleanup, EDT and OCC insertion, coverage analysis, pattern generation, serial and parallel scan pattern simulations. And these are the configurations which are actually there in our level 3 projects. Okay. And then we will be covering all these things. So what is hierarchical scan? What is the TSDB flow? Okay, so we'll be working on MBIST and IJTAG insertion. So here we'll be doing the IJTAG insertion, MBIST and IJTAG insertion, OCC insertion. All those things will be coming in level 3 and level 4 projects, but not in level 1 and level 2. In level 3 and level 4 projects, MBIST, IJTAG, OCC insertions, all those things will be covered. So MBIST and IJTAG insertion, so all these components we will be adding it up, grouping of memories. So how to divide the memories in different steps. So how to control all these signals using TDRs. Okay. So what is the MBIST pattern specification? If in case your MBIST simulation fails, how to do the debug. EDT and OCC insertion in RTL, scan insertion, and then scan wrappers. Whenever you go for hierarchical scan, you'll be having scan wrappers. So scan wrappers, what are shared wrapper, what are dedicated wrapper, what are wrapper chains, all those things we will understand. Okay, and then we'll be understanding about the in-test and X-test concepts in ATPG. These are all hierarchical. These are all specific to hierarchical scan wrappers, in-test and X-test concepts, pattern retargeting. So all those things, practicals as well as theoretical part we will be covering. And level 4 projects will be a flat scan. We'll be having a flop count of 44K. So MBIS, scan chain stitching, DRC cleanup, EDT, OCC insertion, ATPG coverage analysis, all those things we'll be doing. So this is the configuration. And things to learn will be understanding what are the differences between the hierarchical scan and flat scan. So how to debug the simulation mismatches, MBIS simulation mismatches. So ping mux logic, what is it? We'll be understanding scan insertion and ATPG. We will understand what is the difference between level 3 and level 4 projects. So level 3 is hierarchical scan, level 4 is flat scan. So what are the differences between the two? So you will be able to understand. Okay. So yeah. Okay, now let me just now I have just given you an idea on what all the topics will be covered in our theory and labs. So apart from that, I will be covering some extra topics. Like in the previous batch, some of the students had asked some extra topics like LBIST. I'll be giving you an overview about it. LBIST, RAM sequential, IEEE 1500 standard, and one of your batchmate has asked for silicon debug, and then ROM MBIST. Okay, so these are all some of the topics which is not a part of our syllabus, but I will be covering it up because an overview I'll be giving you, because like LBIST, these are all some of the topics which old batch students had requested. So LBIST, RAM sequential, IEEE 1500 standard, ROM MBIST, and then one of your classmates had requested for silicon debug. Okay, so these things I'll be covering. So SSN, whether it is covered in our course? No, Nitin, SSN is not covered in our course. So if possible, then I can try to give you an overview about it if possible. But as of now, I cannot guarantee. So as of now, these are the extra topics which I can guarantee that I will be able to cover in the course. So SSN, if possible, I can give you a theoretical overview. Okay, I'll try to give you a theoretical overview if possible, but I cannot guarantee that. If possible, I'll try to give you a theoretical overview, but it's not covered in our syllabus. Okay. And JTAG and IJTAG insertion will also be done in Tessent. Yes, for all the things we'll be making use of Tessent tools. Okay, except synthesis, everything will be making use of Tessent tools. So Nandan, can you please repeat again? Okay. Which one do you want me to repeat? the labs part is it, you will be able to understand. So as of now, like I've just told what all the things we will be covering in the labs. So when we do the lab part, you will be able to understand what each thing is. So as of now, I just told you the terminologies. Okay, as of now, I just gave you some terminologies. Okay, so you will be able to understand it. What are all these things? You will be able to understand it when we do the lab part. Okay, so yeah, learning to use Tessentis for synopsis is also required, because in the Shilpa, like in our course, we will be making use of Tessent tools. If you require synopsis tools, then you can like contact the institute management. They can arrange you some one-to-one sessions for synopsis, or else if required, I can just try to give you an overview on synopsis. Okay, 1 or 2 sessions I can spend, and I can try to give you an overview on how we can do the labs using synopsis tools. But our main course will be using Tessent tools. So synopsis tools, I can give you an 1 or 2 sessions I can spend, and I can give you an overview. So when you attend the course, you can just remind me once. Okay, when you attend the course, you can remind me. So 1 or 2 sessions at the end of the course, I will teach how you can do the synopsis tools, how the flows would be there using synopsis tools. But our main course will be using Tessent tools. Okay, so synopsis tools at the end of the course, 1 or 2 sessions I can spend, and I can cover them. Okay, so please remind me, Shilpa, and like Chetan, you had requested for silicon debug, right? So if in case I didn't cover them, means if I forget about that, please remind me when you are there in the batch. You can remind me. So Chetan, you had requested for silicon debug, and Shilpa, you had requested for synopsis tools, right? So when you're there in the batch, you can just remind me if in case I forget to cover them. Okay. So what is covered in AI focused course? So as of now, AI focused in the institutes, as far as I know, only DV is covered using like AI is actually like DV course is only covered through AI. Okay, for AI training is actually given in the DV course. So as of now, as far as I know, in DFT course, AI is not implemented. But you can once check that with Vaibhav sir, because I gave the detail based on my knowledge, but I'm not sure, 100% sure about it. So can you please contact Vaibhav sir? So sir will be able to tell whether DFT course is also AI focused. So as far as I know, DV course is AI focused. We have not yet developed the AI part. So, but I'm not sure about it. So you can once check that with Vaibhav sir also. Okay. And which tool we will be using? Yeah, we will be making use of the Tessent tools in our course. So this is the tools which we will be making use of it in our course. Okay, so we'll be making use of Tessent MBIST, Tessent scan for MBIST, Tessent MBIST, scan, Tessent scan, EDT Tessent test compress, ATPG Tessent test compress, and simulation Questa sim. Okay, so these are the tools which we will be using. So if in case you want to learn synopsis tools, then I'll just give you 1 or 2 sessions at the end of the course. I will give you an overview on how these flows will be done using synopsis tools. But in our course, majorly in our course, mainly we will be, in our course, we will be making use of Tessent tools. In our labs, we'll be making use of Tessent tools. If in case you're interested to learn synopsis, 1 or 2 sessions at the end of the course I will spend, and I will try to give you the flows. Really, I will teach you the flows from synopsis. Okay. So yeah. So if in case you have any questions, can you please post it in your individual group, either me or from the admin team side, or the manager, they will be addressing your queries. So I'm actually having another session at 4:45. So like I will end this session now. So like if in case you have any questions related to the course, any course content or anything, you can like message in your individual group. So respective people will answer your question. Should we learn those commands in Tessent, or how is it? Like there is no, like I will tell you during the course. So some important commands you have to know. So like say for example, the interviewer might ask, what is the command to do the scan insertion means? You should be able to tell insert test logic. So like that's some important commands you have to know. So what are the important commands? What are the important commands? will be asked from an interview point of view. I will tell it when I do the each lab. So those important commands, if you understand, that would be sufficient. Okay. Will you be taking theory and labs? That I'm not sure. That will be decided by the management. Okay. So like which trainer will be allotted, it will be decided by the management. So I'm not sure about it. Okay. So yeah. Okay. So yeah, thank you all. We will end today's class because I'm having another session at 4:45. Any doubts related to the course content or any doubts you have related to today's demo session, you can post in your individual group. A group would have been created with your VLSI Guru ID and your name. So you can post your message there. I will address your queries. Or else if it is like any other person from management side, they will also address your queries. Okay. So yeah, thank you all. I'll end today's class now. Is there any much differences between Tessent and Synopsys? Commands would be different, and then the architectures would be different. Like compression architecture of Tessent is EDT, whereas in Synopsys it will be codec. So those architectures will be different. Tessent MBIST architecture and SMS MBIST architecture will be different. Commands and then architectures will be different, but the concept will remain the same. Concept will be same. Commands will be different, and architectures, the way in which it is done, compression concept will be same, but how it is implemented, so that would be different between Tessent and Synopsys. Same way, MBIST concept will be same, but how it is implemented between Tessent and Synopsys, those architectures would be different. Okay. So any questions, please post it in your individual group. So thank you all. We'll end today's class.